So we are set to begin chapter 8. Chapter 8 really begins to open the door to the future. We said that about chapter 7, and it's true because chapter 7 really rolls into chapter 8 nicely. But chapter 8 takes the other side of the road and really does some pretty good stuff with it, and will show you a lot of what you're going to need to know in the future. Having said that, let me back up one little moment and just pick up something that we've said some time ago. But when we talked about direct variation, and it's just a review piece. It has really nothing to do with the material we're about to do. It's just the question is, which one of these three graphs is an example of direct variation? And this has a negative slope. This has a positive slope. This has a positive slope. And this has an undefined slope. I hope you would know that. Now, having said that, I can tell you that's not what this problem's about. It's just another thing that we can take note of. The key to this problem, as far as trying to figure out about the direct variation, is that all direct variation equations are of the form y equal kx, where k is the constant of variation. It's also the slope. It's the slope. I mean, it's in the place of slope when you do y equal mx plus b. But the difference here, the strange thing is, there's no b. There's no piece here after the x. And that's because the y-intercept and the x-intercept is right here at the origin. So that tells us that this graph is direct variation because it passes through the origin. That's a big deal. It probably will be on the SOL test, and so I like to make sure that we deal with that a few times along the way in review. So coming back to here, we're going to begin the process of factoring. Now, you factored in elementary school. You talked about factoring and finding the factors of numbers, and we're going to review that here in a minute. But finding the factors of a number is one thing. Finding greatest common factors is a little different. It's a little more because you find the factors of a number, but here we're going to find the greatest common factors. And we're not going to just do it of numbers. We're going to do it of monomials, which can consist of variables as well. So factored form, when they say factored form, they're saying a monomial expresses a product of prime numbers and variables in which no variable has an exponent greater than 1. Let me just show you one here that they would be looking for, and we'll get back to this in a bit. But here is 18x squared y. 18x squared y broken down into factors looks like this. And you can see the 18 is here because 2 times 3 times 3, that's 18. But all these are prime numbers, so you wouldn't put like 2 times 9 or 3 times 6, although those are 18. So you want to break it down into prime numbers. And then you have x times x, which is the x squared. And then you have y times y times y, which is the y cubed. So when they say factored completely up here, or factored form, it's actually what this one is, that's what they're saying. Okay? Then we deal with greatest common factor. The product of the prime factor is common to 2 or more integers. So by definition, it goes back, talks about those prime factors. So let's look at finding factors. Factors of 6, for example, are 1 times 6 and 2 times 3. Do you agree that 1, 2, 3, and 6 are all factors of 6? There's more than one way to get 6 using integers, positive integers. We could go into the negative world, and of course that would work as well. If we look at a number like 36, you can see there's a lot what I call pairs of factors. So you got 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. That should begin to come natural to you as you go through this chapter because we're going to do these kinds of things so much. But the pairs of factors, remember I'm saying it that way, the pairs of factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. So if we wanted to talk about the factors of 36, there'd be 1 2, 3, 4, 6, 9, 12, 18, and 36. And I got all of those from this list, okay, from the pairs of factors. I just wrote them out in a linear form here, okay. Now, we also, in the previous chapter, took note of the fact that we can multiply two binomials. It's a multiplication, and we use FOIL, and we pull the O and the I together, and we would get something like this. So what we're going to learn about in this chapter, and I told you that's what would happen, this will be the problem, this will be the answer. In other words, this is our trinomial or quadrilateral, and these are its factors. These are its factors. So the factors of x squared plus 5x plus 6 are these two things. So that's something you've talked about before as far as factors and greatest common factors. But of course, this is going to be different than what you've talked about before. So let's back up and let's talk about finding the factors of 12. First of all, the pairs of factors of 12 are 1 and 12, 2 and 6, 3 and 4. So the factors of 12 are 1, 2, 3, 4, 6, and 12. Those are the factors of 12. Those are not prime numbers. Well, the first three are prime numbers because they are, but they're not all prime numbers, but those are all of the factors of 12. Now, if we wanted to talk about breaking 12 down into prime numbers, like we saw here, when they took the 18 and broke it down into those three numbers, then it's a little different. One method that I have seen students do in school is 12 is like 2 times 6. And 2 is a prime number. And then 6 is 2 times 3. So the prime factorization of 12 is 2 times 2 times 3. And that fits the other example we'd seen. I like to do it this way, and it's probably the way that I'm going to do it when I need to do this. Although the pairs of factors are kind of my favorite thing that we do, and we'll use it a lot in this chapter. But this is sort of an upside down division looking thing. And by the way, let me say that prime numbers are numbers like 2, 3, 5, 7, 11, 13, 17, 19. You should know those. But prime numbers are numbers that only have one in themselves as factors. So the smallest prime number in the world is 2. 2 goes into 12 6 times. 6 is not a prime number, so we repeat the process. Smallest prime number is 2, and 2 goes into 6 3 times. And that is effectively what we have here, doing it a different way. So I'm probably going to do it more often this way, like I said, when we need to do it. It'll be easier for us to look at that way. So 18, I'm first going to talk about the pairs of factors because we need to know how to do that, like I said in this chapter a lot. 1 and 18, 2 and 9, 3 and 6. 4 does not work, 5 does not work, and then I'm back around to 6, so I'm done. Those are the pairs of factors of 18. So the factors of 18 are 1, 2, 3, 6, 9, and 18. But let's talk about the prime factors. Or let's do the prime factorization of 18. Remember, the prime numbers are numbers like 2, 3, 5, 7, so on. Smallest prime number in the world is 2. 2 does go into 18 because it's even 9 times. 9 is not a prime number, but 9 will not divide by 2. So what's the next prime number? 3. How many times will 3 go into 9? 3 times. So that is the prime factorization of 18. So next, I'm going to ask for the greatest common factors. greatest common factors. Let's go back to here. And we'll look at this two ways. First, I'm going to look at the pairs of factors of 18. Okay, pairs. We said 12. Well, the pairs which gives us the factors. From the pairs, we'll do it this way. So we said 2 for 12. Let me just make that a little nicer for you. So for 12, we're saying 1, 2, 3, 6, and 12. Lost the 4. Gosh. I knew there was something missing. And for the pairs of factors of 18, you can see we have these, which was 1, 2, 3, 4 did not go, 6, 9, and 18. Yep. All right. So these are the factors that come from the pairs. So we're talking about the greatest common. Is it obvious to you that the greatest common is 6? That's not new math. That's old math. You should know that. But I want to look at it a different way because of where we're going. Let's look at the prime factorization of 12. We said 12 was 2 times 2 times 3. Or I could call it 2 squared times 3. 18 is 2 times 3 times 3, or we could call it 2 times 3 squared. I know this is new, so be patient. Be patient with yourself. Be patient with me. Be patient with the material. So look at these factors here. And I want to ask the question, we're dealing with greatest common factor. I'm going to ask the question, where is it found the least? And that's kind of bizarre because we're talking about greatest common. But if I've got 3 $5 bills and you've got 1, we don't have 3 in common, we've got 1 in common. So greatest common is the most we have in common. I've got 3, you've got 1. We've only got 1 in common. So the 2, where's it found the most or the least? The 2. Where's 3 found the least? The 3. When I say the least, you got the idea here of 2 squared and 2 to the first. Which one's the smallest? 2 to the first. Here you got 3 to the first and 3 to the second. Where is it the smallest or the least? 3 to the first. What is 2 times 3? 6. You're like, well, then why don't we just do it this way because it's easier that way? Of course it is. I just want you to see it. I mean, I got reason for you to see it, but I just want you to see it. Okay. So let's go back to this, and we have a different problem. So greatest common factor. Let's talk about 18. 18, the factors we said were 1, 2, 3, 6, 9, and 18. 24, the pairs of factors are 1 and 24, 2 and 12, 3 and 8, 4 and 6. So the factors are 1, 2, 3, 4, 6, 8, 12, 24. I went down one way and back up the other, and that's where I got those numbers. Is it obvious to you that the greatest common factor is 6 again? Okay? Now, let's look at it again in terms of the prime factorization. We said 18 was 2 times 3 squared. 24, I'll just have to do it right here real quick. Divides by 2, 12. Divides by 2, 6. Divides by 2, 3. So 24 is 2 cubed times 3. So remember my question was, where's it found the least? Well, here and here, which is 6, which is the answer. We got that other way. So I just want you to see these two ways. They both have value to us in the work that we're going to do. And the more proficient we can become at finding factors, prime factors, common factors, the easier this other material is going to be, because we do have other things to consider. So this problem asks us to factor this completely. Now, we have already looked at that answer, and we've already looked at this process, because we've already said that 18 is 2 times 3 times 3. And then x squared is x times x, and y cubed is y times y times y. Okay? And we looked at this several times already, this slide, a couple of times at least. So that is the factored form of 18x squared y cubed. So look at this one. What's the factored form of the 15? Well, the way I do this, 3 won't go, but 2 won't go, 2 is the smallest prime, but 3 will. And so it's 3 times 5, which means it's got to be one of these answers, because this one they didn't break up the 15. You can see that. Next, we got the a cubed, and so there should be 1, 2, 3 a's. There are. Here they didn't break that up, so that's out. Here we have 1, 2, 3 a's. That's good. So b and d still have a chance. And then the b squared, b times b, they broke that up. That's good. Here they didn't break it up. Answer is b. And I say break up, that's what we're doing here, really. We're pulling these things apart. That's what we're going to be doing. So we have 3x squared plus 9x. So we're being asked to find the GCF. Instead of saying 3x squared comma 9x, these two things, they could have done it that way, find the GCF of these two things. They've given it to us in binomial form, because that's where we're going. That's where we're going. So when we talk about greatest common factor here in algebra class, we should recognize that GCFs have the potential for a numeric part and an algebraic part. Numeric and an algebraic part. So let's look at the numeric part first. When we consider the 3 and the 9, what is the greatest common factor for 3 and 9? I hope you said 3. Okay? 3. From elementary school. The biggest number to go into both of them, greatest common factor for 3 and 9, 3. Then look at the x squared and the x. And remember the question. Where is it found the least? Where is x found the least? Because you have x squared and x to the first. So it's x to the first. That's the answer to that question. This is the GCF. So, look at these two. We have two monomials. They are monomials. And they've asked us to find the GCF of these two. Remember we said it could have a numeric part and an algebraic part. So let's talk about the numeric part. What's the biggest number that will go into 27 and 15? Now, if you need to, you can sit down and write these things out, like the way I did in the earlier slides. You probably know that the greatest number that will go into 27 and 15 is 3. Because 9 won't go into 15, 5 won't go into 27, so some of the other factors won't work. And then we ask the question. In regard to the variables, where is it found the least? Look at the A. Where's it found the least? A squared or A to the first? Where's B found the least? B or B squared? And do you recognize they do not have a C in common? They don't have a C in common. So C cannot be part of the common factor because they don't have a C in common. So the answer is 3AB. Now, I do want to draw your attention to this because this is what I was doing earlier, and we can still be doing that in these problems. They took and they purposely broke this down in the prime factors. And then they said, where's 3 found the least? And the answer was here. And then they said, where's 5 found the least? Well, they don't have a 5 in common, do they? So that's why 3 is the numeric part of the GCF. Then they looked at the A's, and they said they got an A in common here, and they got a B in common here. Where's it found the least? Let me erase that, and you can look at it again. All right? So 3AB, which is exactly what we got, looking at it a slightly different way. So 39x squared y cubed and 26x y to the fourth. Greatest common factor. Biggest numbers are going to 39 and 26. We don't walk around every day thinking about 13, but that's the answer, numeric answer. You just don't think about 13 factors or multiples of 13 very often. But now that we've done that, because that's a bridge you would need to cross, then we're going to be looking at the x's. And we're going to ask that question. Where's it found the least? The x squared or the x to the first? And of course it's x. And both of these have x. So then we look at the y cubed. They do, or with the y's, the y cubed and y to the fourth. They do have a y in common, that's for sure. Where's it found the least? The y cubed or y to the fourth? The y cubed, of course. So that's not it. That is, answer is D. So the lengths of the sides of a triangle are blip, blip, and blip. Find the greatest common factor of the 3 lengths. It's just, a stretching here to try to make this relevant to the world we live in. So here we go. We have these 3 things. Oh, we have 3 things. Oh, we have 3 things. So we have to consider 3 things in common factor. So let's look at the 12, the 8, and the 16. What's the biggest number that'll go into all 3 of them? What's the greatest common factor of 12, 8, and 16? I hope, with a little bit of thought, you can see that it's 4. Because like a 6 will go into 12, but it won't go into this. No, it won't go into that either. 8 will go into these 2, but it won't go into the 12. The biggest thing to go into all of them, 4. Next, we got to look at the variables and ask the question about the least. Do they have a W in common? Yes. Where's it found the least? W to the first. That happened here and here, so it's W. Do they have a Z in common? The answer is yes. Where's it found the least? Well, it's Z, and that's happens here and here, right? Because this is Z squared, but we're not looking for the most, we're looking for the least, so it's that. 4WZ is the greatest common factor of these 3 terms. 4WZ. Maria's making bracelets with large and small beads. She has 20 large beads and 96 small beads. What is the greatest number of bracelets she can make without, I had to put that word in there, the out, because they left it out, without having any beads left over. So, in other words, we're looking for a GCF. Now, we may not think about that. They do use the word greater right there. But we're looking for a GCF. What's the greatest common factor of 20 and 96? Now, we could do prime factorization of those two numbers, and we could do it that way. I'm going to do the pairs of factors again because, like I said, we do a lot of stuff with the pairs of factors in this chapter. 20 and 10. 3 does not work. 4 and 5. And that's all for 20. 96 is 1 and 96. There's a lot. But you can use a calculator, so it's not, 2 and 48. 3 and 32. 4 and 24. 5 does not work. 6 and 16. 7 does not work. 8 and 12. 9 does not work. 10 does not work. 11 does not work. And we're back around to the numbers on this side. So those are the pairs of factors. Well, let me make a point with you here. They have 1 in common. They have 2 in common. They have 4 in common. And that's all they got in common. What's the greatest one they got in common? 4. Answer is B.